In the realm of automotive engineering, few challenges are as formidable as designing a hypercar capable of extreme speeds without a fixed roof. For decades, the pursuit of maximum velocity has been synonymous with enclosed, aerodynamically optimized forms. Yet, Bugatti, a marque defined by pushing boundaries, sought to reconcile this inherent contradiction with the Mistral. This vehicle was conceived not merely as an open-top variant, but as the world's fastest convertible, targeting speeds exceeding 400 km per hour. This objective immediately set it apart, demanding a reimagining of fundamental aerodynamic principles and structural integrity. Bugatti's reputation is built upon a consistent pursuit of top speed, exemplified by models like the Veyron and Chiron. Each iteration has incrementally pushed the limits of automotive performance. However, according to automotive historians and Bugatti's own design statements, these vehicles were predominantly developed as coupes, where a rigid roof forms a crucial part of the aerodynamic and structural package. The Mistral, as Bugatti's final W16-powered roadster, represented a deliberate shift, injecting the brand's speed philosophy into an open-top configuration. This decision presented an unprecedented set of engineering hurdles that required innovative solutions. The primary challenge in designing a high-speed convertible lies in managing airflow. A fixed roof provides a clean, predictable surface for air to flow over, crucial for minimizing drag and generating downforce. Removing it introduces significant aerodynamic disruption. As Dr. Wajid Khan, an expert in automotive aerodynamics, notes, the open cabin creates a cavity that generates turbulent eddies, increasing drag and compromising stability at elevated speeds. This turbulence can not only slow the car but also make it unstable and uncomfortable for occupants. Bugatti's engineers had to address these fundamental issues while preserving the Mistral's aggressive performance targets. Beyond aerodynamics, structural rigidity becomes a critical concern for a high-speed convertible. In a traditional coupe, the roof forms a vital part of the chassis' torsional stiffness, connecting the A and C pillars. Removing this structural element can lead to significant chassis flex, particularly during high-speed cornering or under extreme acceleration. This flex compromises handling, precision, and safety. According to Bugatti's chief engineer, Emilio Ferraris, the Mistral's monocoque structure had to be fundamentally re-engineered to compensate for the absence of a fixed roof, ensuring unyielding stiffness at speeds approaching 400 km per hour. The wind tunnel became an indispensable tool in the Mistral's development. It allowed Bugatti engineers to precisely visualize and measure airflow patterns, pressure distribution, and drag forces at various speeds. Unlike digital simulations, physical wind tunnel testing provides empirical data that accounts for real-world fluid dynamics. Bugatti reportedly utilized advanced rolling road wind tunnels, simulating ground effect more accurately, which is crucial for a car designed to generate significant downforce. Initial tests, as per Bugatti's technical reports, revealed substantial lift and cabin turbulence that needed to be mitigated through extensive design iterations. Complementing physical wind tunnel testing, computational fluid dynamics, or CFD, played a pivotal role. CFD allows engineers to digitally simulate complex airflow scenarios, providing immediate feedback on design changes without the time and cost of physical prototyping. For the Mistral, CFD was instrumental in rapidly exploring thousands of design variations for elements like the windscreen, air intakes, and rear diffuser. According to Bugatti's development team, early CFD models helped identify critical areas of turbulence around the passenger compartment, guiding the initial conceptual design away from less efficient solutions before expensive physical models were even constructed. A core objective for the Mistral was to ensure occupant comfort, even at speeds traditionally associated with fixed-roof vehicles. This necessitated intricate cabin airflow management. Bugatti engineers, through extensive simulations and physical tests, developed a unique windscreen and side window design to divert the main airstream up and over the occupants. Furthermore, the rear deck features a raised section and subtle air channels designed to minimize backdraft and turbulence behind the seats. According to Bugatti's design director, Akeman Shait, every surface, from the A-pillars to the headrests, was sculpted to guide air cleanly away from the cabin. The Mistral's distinctive air intakes, positioned directly behind the headrests, are not merely aesthetic elements, they are crucial for engine cooling and air supply. In a convertible, the removal of the roof changes the pressure zones around the engine bay. Bugatti's solution involved a ram air effect, where the placement and shape of these intakes actively force air into the W16 engine and cooling systems as speed increases. These intakes also integrate a secondary function, serving as rollover protection, reinforcing the vehicle's safety credentials without compromising performance. Engineers verified their efficiency through high-speed track testing. To maintain stability at 400+ km/h, the Mistral required substantial downforce without excessive drag. This was achieved through a meticulously designed underbody, a prominent rear diffuser, and an adaptive rear wing. Unlike traditional convertible designs that often prioritize aesthetics over aero, Bugatti's approach was performance-driven. According to internal documents, the underbody was sculpted to create a Venturi effect, accelerating air beneath the car to generate suction. The rear diffuser then expands this air volume, creating a low-pressure zone that pulls the car onto the road. The active rear wing adjusts its angle to optimize downforce or reduce drag based on speed. Overcoming the structural deficit of removing a roof demanded extensive chassis reinforcement. Bugatti engineers reportedly focused on strengthening the carbon fiber monocoque itself, integrating new structural elements into the sills and A-pillars. Torsional rigidity, a measure of a chassis' resistance to twisting forces, was a key metric. Sources indicate that despite the open-top design, the Mistral approaches the torsional stiffness of its coupe counterparts, a remarkable feat. This was achieved through meticulous layering of carbon fiber composites and strategic use of high-strength alloys in critical load-bearing areas, ensuring precise handling at extreme speeds. Even seemingly minor details on the Mistral underwent rigorous aerodynamic scrutiny. Side mirrors, for instance, are not simply attached, they are carefully sculpted to minimize drag and prevent adverse airflow disturbances from reaching the cabin. Similarly, every vent and aperture across the car's body serves a specific aerodynamic purpose, whether it's managing turbulent air around the wheels or directing cooling air efficiently. Bugatti's philosophy, as documented by automotive design journals, emphasizes that form follows function, but often, the most beautiful form is the most aerodynamically efficient. This intricate attention to detail underscores the engineering intensity. Achieving the Mistral speed targets required not just clever design, but also advanced material science. The extensive use of carbon fiber composites throughout the monocoque, body panels, and aerodynamic elements was fundamental. Carbon fiber offers an exceptional strength-to-weight ratio, crucial for both structural rigidity and minimizing overall mass. Lightweight aluminum alloys are utilized in suspension components and subframes. Bugatti engineers reportedly selected materials not only for their strength but also for their thermal properties, essential for handling the immense heat generated by the W16 engine at sustained high speeds. This material selection is paramount for safety and longevity. The development of the Mistral was characterized by a highly iterative design and testing process. Engineers and designers worked in a continuous loop, moving from digital simulation to scale models, then to full-size prototypes. Each stage informed the next. If wind tunnel tests revealed unexpected turbulence, the design team would revisit the CFD models, refine the surfaces, and retest. This relentless cycle of design, simulate, build, test, refine is standard in hypercar development, but for an open-top aiming for these speeds, the number of iterations was reportedly far greater. This dedication underscores the complexity of achieving the stated performance goals. The ultimate validation of Bugatti's aerodynamic and structural solutions came during high-speed testing. While simulated environments provide invaluable data, the real world introduces variables like crosswinds, temperature fluctuations, and road surface imperfections. Bugatti reportedly conducted extensive testing on dedicated high-speed tracks, pushing the Mistral to its limits. Test drivers provided crucial feedback on stability, steering response, and cabin comfort at extreme velocities. Data loggers measured every parameter, from suspension compression to localized air pressures, ensuring that the theoretical models translated accurately into real-world performance. The target of exceeding 400 km per hour, or 250 miles per hour, without a fixed roof was a benchmark many considered impossible. This speed places immense strain on every component, from tires to suspension, and fundamentally challenges aerodynamic stability. To achieve this, Bugatti engineers had to ensure that the Mistral's drag coefficient remained exceptionally low despite the open cabin. They also needed to ensure sufficient downforce to keep the car firmly planted, preventing lift. The meticulous development process confirms that this wasn't a hypothetical aspiration but a rigorously engineered goal, pushing the very definition of a roadster. Powering the Bugatti Mistral is the iconic 8.0-liter quad-turbocharged W16 engine, producing 1,600 horsepower. While the primary focus here is aerodynamics, it's crucial to acknowledge that this immense power unit provides the necessary thrust to overcome aerodynamic drag at extreme speeds. The engine's thermal management, particularly in an open-top configuration, required specific aerodynamic considerations for cooling. According to Bugatti, the enlarged horseshoe grille and redesigned side intakes were optimized not only for airflow but also to feed the W16 with the vast quantities of air needed for both combustion and cooling, ensuring sustained performance during high-speed runs. The design of the Bugatti Mistral masterfully blends breathtaking aesthetics with uncompromising aerodynamic functionality. Every curve, line, and surface is not just visually appealing but serves a critical purpose in guiding air, generating downforce, or mitigating turbulence. The designers, working hand-in-hand with aerodynamicists, ensured that the pursuit of speed did not detract from the car's sculptural beauty. This synergy is evident in elements like the distinctive X-motif taillights, which, beyond their striking appearance, also aid in extracting hot air and managing wake turbulence. It is a testament to Bugatti's ability to integrate complex engineering solutions seamlessly into an elegant form. The Bugatti Mistral stands as a profound achievement in automotive engineering. It demonstrates that the traditional limitations of convertible design, compromised aerodynamics and structural rigidity, can be overcome through relentless innovation and a no-compromise approach. By leveraging advanced wind tunnel technology, sophisticated CFD simulations, and a deep understanding of fluid dynamics, Bugatti has not only created a beautiful open-top hypercar but one that maintains the brand's legendary pursuit of extreme speed. The Mistral is, by Bugatti's own declaration, the fastest open-top production car ever conceived, a benchmark for future generations of high-performance roadsters.